Welcome to Required Practical 9. In this practical, you are expected to investigate the charging and discharging of capacitors with an aim to plot a log linear graph to find the value of RC. Here we have a FET simulation where we have a capacitor and an incandescent bulb. When you close the switch with the charged capacitor, it discharges through the bulb, and you can see that the voltage is changing as time goes by. We can charge the capacitor back up again by connecting it to the power supply and discharge it once again through the bulb. Now, in this simulation, we do not know the resistance of that bulb, but it does have resistance, and this capacitor has a capacitance, which is known. So we can do an investigation using this data to find the resistance of this incandescent bulb. First of all, we charge up the capacitor. Notice that the voltmeter is connected to the positive and negative plate using these probes. What I will do is I will start the timer, and when it gets to a convenient point, such as the 5-second mark, I will flick the switch and begin to discharge the capacitor through the lamp. What I'd like you to do is to let the video play. I'm going to flick the switch when we get to 5 seconds, and I'd like you, every 5 seconds after that, to take a reading of the voltage without pausing the video. We've charged the capacitor. We've zeroed the time. Here we go. Take a reading now, 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 and now, and stop. Now what I'd like you to do is I'd like you to rewind the video and look at the data that you get when you're able to pause video and see how much more accurately you can get that data. And you'll notice that when you have a voltmeter rapidly changing like this, you are unable to read some of these numbers, and you don't get particularly accurate results. If you were doing this in the lab, you wouldn't be able to look at these numbers, you wouldn't be able to read them easily unless you videoed it. In fact, it would be easier to use an analog meter for this type of experiment. However, if you have a digital meter, the best thing to do is to take a video recording. Make a note of the voltage and the times that you gathered, and then we'll have a look at how to analyse that information. So what I've done here is I've done that experiment. I've recorded the time, and I've done it from a 0 mark, 5 seconds later, 10 seconds later, 15, 20. We started with a voltage of 1.5, and I did my best to get these data readings here, despite the fact that the values were changing rather quickly. I highlighted it, went to Insert, and a scatter graph, and this is the graph that we end up with. You can see that it is an exponential curve. When you do this, you should right-click on your data points and click on Add Trend Line. You can then select that it's an exponential shape. And you should see the decline in voltage as time passes. We have a very steep graph initially, and then it goes shallow. The rate of change of voltage is quick and then slow. If we compare that to the data that we get when we are able to pause the video, you can see a slight difference. So here was my original data, and here is the data that is more accurate because I was able to pause the recording. And here we have different values compared with what we had previously. It's the same file, it's the same data file, so they should be the same, but they're not. And I've calculated the percentage difference up here. And you can see that as we move along, we get further and further away from the true value. And when I plot the new values against the old, the new values in orange, you can see they do differ. If we then do some calculations with these values and plot a new graph, we can get the value of the resistance of the incandescent bulb. So let's have a look how we do that. We know that the voltage at any one point in time is equal to the original voltage multiplied by some factor. It might be at 85% its original value, or 33% of its original value, but we are multiplying by some value that allows us to calculate this. And that value, that decimal, is calculated by taking the number e, which is a very special number to do with the rate of change, to the power minus the number of seconds which have gone by over the value of the resistor multiplied by the value of the capacitor. And it is this here, this R, that we are trying to calculate for this circuit. The capacitance is known, but we do not know the resistance of that incandescent bulb. Notice that this is a simulation, it's not a real experiment, and therefore the value of that resistance might not be realistic. We're going to calculate it anyway. So the way that we can access this power is we need to bring the power down by removing e to the power of. So let's isolate this part of the equation by rearranging. Okay. In order to bring this down and remove the e, we need to take the natural logarithm. If you're doing A-level mathematics, you will understand this. If you're not, please don't worry. You don't need to understand what you're about to do, but we are going to do the natural logarithm of both sides of this equation. There is no e on the left side, so the natural logarithm is performed on these values. And on the right-hand side, when we take the natural logarithm of that side, it eliminates the e and brings the power down. I'm going to rewrite this. As that. Now, according to the rules of logarithms, I can rewrite this term as the natural logarithm of the voltage minus the natural logarithm of the original voltage. And that is still equal to this. I'm now going to rearrange this so that it's in the form of y equals mx plus c. There's our y. There's our m. Here's our x. And there's our c. So we're going to plot this on the y-axis. We're going to plot this on the x-axis. Here is our gradient, and here is our y-intercept. Let's have a look at the data in Excel. Here on the right-hand side, I have my values of the natural logarithm of the voltage. And you can see that I've used a formula to do this, and I've used the more accurate set of data. If we click along, we can see that I'm using all of the values. Some of them are positive, and some of them are negative. But when I plot them against time, you can see that it makes a straight line graph. And when I click on my data values, and I went to add trend line, I selected a linear trend line. I can also select to display the equation on the chart. Now, if you're doing this by hand, you will need to use the rise over run method to calculate the gradient of your line. If you're doing it using Excel, then you can display the equation on the chart and view the value for gradient. There it is. So now that I have my value for gradient, I know that that value will be minus 1 over RC. So I'm going to type my value in here. It's negative 0.2138, and I've done some calculations. This is my minus 1 over RC, which is equal to the gradient. I then take the inverse and make that number positive, and I get 4.677. Notice that if you calculate 5 RCs, 5 time constants, you should get the time for the capacitor to completely discharge. So let's do that now. And that is roughly how long our experiment went for in seconds. And in that experiment time, the capacitor did completely discharge. So this is looking like it's accurate so far. On the simulation, the value for capacitance was 0.89 picofarads, which is rather small. If we then take 4.677268 and divide that by our capacitance, then we get a value for resistance, which is an extremely large number of ohms. In fact, it's approximately 5.3 teraohms, which is a little unreasonable. You wouldn't really get that in a normal investigation, but this is just a simulation. If we have a look at another type of simulation, then we can look at the sort of data that you will be getting in the classroom. Here we have a piece of software called Crocodile Clips, and you can download this for free. On the left-hand side, I have a circuit set up to investigate a discharging capacitor, and on the right-hand side, I have a circuit set up to investigate a charging capacitor. So in the classroom, you are likely to be setting up these circuits. Here we have a power supply currently set to 5 volts, and we have a toggle switch which is currently connecting the capacitor to that power supply, and there is nothing else in that loop. The capacitor charges very quickly because there's little resistance in that circuit. When I flick the switch, this will toggle over to the right-hand side, connecting the capacitor to this resistor on its own, and the capacitor will discharge through that capacitor. Let's have a look. The voltmeter shows the discharge of the capacitor and the decreasing voltage across the plates. We can have a look at the graph of this behaviour. Let's charge it back up, reset the graph, and discharge. You can see that we're getting the same curve as previously. As part of your investigations, you should be able to draw a discharge curve for a capacitor, usually voltage against time. And you should be able to get the exponential decay curve. You may want to compare this data collected with a digital voltmeter against the data collected with an analog voltmeter. The analog should be easier to collect in real time, whereas the digital you would probably need to take a video recording of. After confirming the values of the resistor or the capacitor, what you may want to do is swap your resistor out for an unknown value and then use your log linear graph to calculate the unknown value. Remember that there will be tolerances involved with both your resistor and your capacitor. Tolerances with resistors tend to be plus or minus 5%, and capacitors plus or minus 20%. If we have a look at the charging circuit, we can do something similar. Here we have the power supply. At the moment, the capacitor is connected in a circuit all by itself. It has discharged. One plate is connected in the circuit to the other plate, and it has a 0 voltage across it. If I flick this switch, then the toggle will move across to the other side, and the capacitor will charge, because it is now in the circuit with the power supply. It will charge through the resistor, so it will charge more slowly than the previous circuit. Let's have a look. As we get closer and closer to the voltage of the power supply, you'll notice that the rate of charge decreases. It is now charging very slowly. At first, it was charging very quickly. This is because it gets harder and harder for more electrons, more negative charges, and also more positive charges to fit onto the plates. Let's have a look at this graph. So here we can see this voltmeter is represented on the blue line, whereas the other circuit is just stationary. And we can see that it's charging rapidly at first, and then the line is becoming more and more shallow as it approaches the 5-volt level. You should be able to set up this circuit and collect enough data to make a graph that shows this exponential growth curve. You might then also want to do a log linear graph, again to calculate any unknown values. Instead of voltmeters, you may wish to connect an oscilloscope and see this curve appear on the screen. There are many different ways to investigate these circuits. In this video, I've shown you a few examples. What I suggest is that you use some of the simulations, or maybe download this software and set up these circuits and play around and investigate yourself.